post-diction. Unlike prediction, where we predict the future, the brain is doing post-diction. It's reconstructing the past. There's evidence that we store information for brief temporal intervals in our perceptual networks, in posterior areas of the brain where we do vision and other sensory processing. And these storage houses are probably used for this reconstruction process. Now, just to remark on this, this too is sort of a footnote, but it's I think somewhat interesting, and time has been neglected in contemporary philosophy of mind. We can ask questions like this. This is an old question. How long is the species present? How long is a moment, a conscious moment? And we're now in a position scientifically to start to answer questions like this. One way to do it is to look for the shortest period of time in which people are accurate about the sequence of two events. So you flash two lights, and you say which one came first, the red light or the blue light. And people are quite good at this. But when you flash them too close together, people start to make errors. And it turns out 80 milliseconds is the time period in which errors start to become rampant. And you might infer from this kind of thing that the temporal moment is 80 milliseconds long. That's how long a moment is. The series of perceptual events that occur within 80 milliseconds are the experiences we have right now. The now is 80 milliseconds long. Now, you might think the now doesn't have any specific temporal breadth. It can stretch and shrink. So people talk about emotion, and they say, when you're terrified, time seems to slow down. If any of you have ever been in an automobile accident, you might experience time slowing down as your car swerves or makes contact with another vehicle. It turns out there's some reason to think that time doesn't slow down. Here's an experiment that David Eagleman was also involved in. What you do is you induce emotion. You scare people, for instance, and then you have them experience something, and you see whether the experience of their that occurs while they're afraid is longer than the experience when they're not afraid. If you measure their memory, the answer seems to be yes. People can tell you, they'll tell you subjectively it seemed longer than in conditions where they weren't afraid. But there's another way to measure subjective length of experience, which is to consider the following assumption. If time extended or expanded when we were afraid, then certain illusions that occur within a certain temporal window should disappear. Temporal resolution should increase. If time is stretching, we should no longer be subject to certain illusions. We should no longer morph together things that are usually morphed together. The little cells making up a movie screen might start to separate if time really slowed down. In horror movies, we should suddenly see the difference between the frames because we're so terrified. But that doesn't happen. There's no evidence whatsoever for an increase in temporal resolution as a function of emotion. So it looks like the reason why time seems longer has to do with recall. We encode more information when we're afraid, and afterwards what we seem to report or recall in memory seems to be richer than the conditions where we weren't afraid. So I think we're in a position to start measuring the duration of the experience, and I think we're in a good position to start to understand the mechanisms that allow for temporal unity. And this long digression was just a way of saying, if you start to look at the science, you don't see any researchers in this area invoking an I. You don't need to. The best accounts of temporal unity, like the best accounts of spatial unity, are stated without any reference to a phenomenal experience of the subject. So I don't think we need a self for binding. Now, a Kantian might say this. A Kantian might say, maybe we don't need it for binding in space and time, but we sure need it for inference. So if you're running an argument, and somebody gives you a premise, and then a second premise, like 2 plus 2. You got 2 at one moment, and the second 2 at another moment, and the plus sign, and now you draw a conclusion, 4. It looks like you need to have a self there, and the self needs to be the same self throughout the argument. One self received the first 2, the same self received the second 2, and because it was one self, that self is able to infer 4. If I whisper 2 into Brian's ear, and then I whisper 2 into Amy's ear, and say, what's the sum? They'll won't be able to report an answer. It has to be one self experiencing both. Now, in response to this, it's worth pointing out that this is the kind of problem that calculators deal with all the time. You certainly need memory, But to credit a calculator with having a self, much less a conscious experience of a self, seems overly generous. It's true there needs to be one organism there, but the idea that there's an I and experience that needs to be present to achieve this unification over inferential time seems to be unsupported. And indeed, if there were such an I, if we wanted to credit a calculator with having an I in some primitive sense, it's not at all clear that it needs to be a phenomenal I, an I available in experience. Okay. When should I stop? Huh?
There's no time limit.
I want to move into some of the science. I didn't want to take quite so much time on the philosophy. So here's let me run through quickly three experimental traditions that are designed to show the presence of a phenomenal I. One of them has to do with the phenomenon of losing yourself. So we've all had this experience where you seem to be so actively engaged in a task that you simply lose yourself. You're no longer aware of yourself for some brief interval. Now, what's going on here when we lose ourselves? There's work by Goldberg and colleagues that has tried to identify the neural basis of losing yourself. And it's interesting for our purposes because if you can find the difference in the brain between the conditions where you've lost yourself and the cases where you haven't, then the cases where you haven't will help you find the neural correlate of the I. After all, there was that I there to be lost. Here's the basic study. You show people a series of images. I'll just do this side here. So you show people a series of images, and you simply ask them, is there an animal present or not? And you either do this very, very quickly, a very fast series of images, or quite slowly. Now, it turns out if you're doing something very, very quickly, you seem to lose yourself. The task is so demanding. You stop thinking about yourself and think solely about these images flashing before you at a great rate. And people say, yeah, I lost myself during that task. The experimenters also did a further task to really get at this. And they said, they gave people the same images, but they said, this time don't tell us whether there's an animal present or not. Just tell us whether you like the thing or not. Is it a positive thing or a negative thing? So somebody might see a lion and say, yeah, that's a positive thing. I like lions. They might see a soccer ball and say, you know, I hate soccer. So they just give, but notice when they're doing this, they have to be thinking directly about the self to give their responses. So in doing this study, Goldberg and colleagues were measuring brain activity. And the basic finding is that there's an area of the brain, which is the left superior frontal gyrus, that seems to be active both when you think about how something, how you like something, and also in these cases where you are given enough time to reflect on whether something is an animal or not. In the condition where the sequence is so fast that you lose yourself, you stop seeing activation in the superior frontal gyrus. And the researchers conclude the superior frontal gyrus is where you have that experience of yourself. That's where the self is. It's right there. But there are problems with this. One problem just has to do with what we know about the superior frontal gyrus. It turns out the superior frontal gyrus is a working memory area. It's involved in storing information for brief intervals, especially when it requires active executive processing. So you're storing that information to think about it, to reflect on it, to use it in some way. Now, this would explain the results. The reason why you lose superior frontal gyrus in the rapid presentation is you don't have time to reflect. So you're not actively using executive working memory. It's a very bottom-up, immediate, knee-jerk response. Now, it turns out that in tasks that require very intensive working memory load, like having to store a very large number of numbers in your head, this area becomes more active. But notice high-load tasks, very demanding tasks, are precisely the ones where we're most likely to lose ourselves. So it turns out that the more demanding the working memory task, the more we lose ourselves, but the more activation you see in this area. So it doesn't look like an area associated with the self. But more generally, the whole idea of losing yourself is, I think, just a sort of figure of speech, and a bad one at that. It's not that there's an experience of a self that gets lost. In the conditions where we lose ourselves, it's something more like we stop engaging in what one might call elaborative processing. So if I give you a picture and ask you, is there an animal there, you might start to think, oh yeah, that's a lion, I like lions, or you might think, lions, I just saw a lion in the zoo, or you might think lions are carnivores, or that lion needs a shave. It might be any number of things you're thinking about that lion. The experience of losing yourself is the experience of being so intensely involved in something that you can't have these